Here we're going to discuss graphing shifted conics. So remember, a conic is one of these types of curves: a circle, an ellipse, a parabola, or a hyperbola. And we have videos for all of these, and it'd be a good idea, if you can't remember what the graphs of these were like, to go ahead and review those videos now. Now, with circles, for example, in the videos on circles, we had examples like this: x minus 2 squared plus y plus 5 squared is equal to 9. Now, we know that this is equation of a circle, and it turns out that the center has been shifted. If you recall from the video on circles, that the center is now 2, -5, and the radius is still 3. So what we're going to see in this video is other conics, in particular the ellipse, that's been written in the shifted form as well. And then once you identify that your original form, you can say, oh, x plus or minus something, y plus or minus something, and that reveals the shift. And every other feature, including the center, or well, in this case for a circle just the center, but for ellipses you have not only the center but the foci, all those, and the vertices, they get shifted as well once you determine what the shift is. Okay, let's see the example that I'm thinking of. So we're going to complete the square to determine whether the graph is an ellipse, a parabola, or a hyperbola. So notice that we have this equation, and our goal is to write it in a standard form so we can reveal the shifts. So the first thing we do is we write, to complete the square, we get the terms with x together, and then the same thing with the terms with y, and then complete the square with those terms. So we have 4x squared minus 24x, and then plus 25y squared plus 250y is equal to, let's write, negative 561, bringing the constant to the right-hand side. Okay, with the terms with containing x, factor out the 4. So 4 times x squared minus 6x, and then plus 25, same thing with the y squared plus 10y equals negative 561. Completing the square, it's going to be 4 times x squared minus 6x plus 9, and then plus, whoops, take that back. Let's erase that. So when you add 9, so remember how this goes. You divide the negative 6 by 2 and you get negative 3, square it, and you get 9. Now you add and subtract 9, and that's the only way you can do it so that you maintain 0 inside the parentheses. And then likewise for the next terms, it's going to be 25y squared plus 10y, and I want half of this is 5, squared is 25. Add and subtract that, so I've added 0 inside the parentheses, is equal to negative 561. And so we're looking at 4 times. Now this part is a perfect square by design, so it's x minus 3 squared, and then we still have minus 9, and then plus 25. Then this part's a perfect square, so it's going to be y plus 5. Quantity squared, take away 25. That take away 25 is this one that still remains, is equal to negative 561. And now we have to distribute the 4. That's why it's important to have that 4 there. So it's going to be 4 times x minus 3 squared minus 36 plus 25 times y plus 5 squared minus 625 is equal to negative 561. Okay, on the left-hand side, we're looking at 4 times x minus 3 quantity squared. Let's combine the constants, so it's going to be plus 25 y plus 5 squared. And then the constants is going to give negative, what is it going to be, 661. And then the right-hand side is negative 561. And then if you add the constant to both sides, we have 4 times x minus 3 squared plus 25 times y plus 5 squared is equal to 100. Okay, now at this stage, remember the standard forms have a 1 on the right-hand side, so we're going to divide both sides by 100. Let's do that here. And then we're going to divide these both by 100, so we're going to get, as our answer, the final result, it's going to be x minus 3 quantity squared over, well, 4 divided by 100 is 25, and then plus y plus 5 squared. And then when you divide 25 by 100, you get 4, and it's equal to 1. Okay, so this is the graph of our conic, or sorry, this is the equation of our conic. And we can see that this is the equation of an ellipse. right? So x squared over a constant plus y squared over a constant equals 1. The graph of that is an ellipse if these are different, which they are. If these are the same, that would be a circle, of course, but they're different, so it's an ellipse. Now I can see that the shift has been, the standard form was just x squared plus y squared. The fact that it's x minus 3, just like with a circle, means that the center has been shifted right 3 and down 5. Okay, let's write this on another page and go ahead and get some information about it. So it was x minus 3 quantity squared over 25 plus y plus 5 squared over 4 is equal to 1. Let's just double check that, make sure I got the right equation. Yeah, we're good. Okay, so there are a few things to note. The larger number tells you your a. So in this case, a is equal to 5. The square root of that the square root of the larger number is a, and the square root of the smaller number is b. So a is 5, b would be 2, and then recall that there's a relationship between a and b that'll give you c. So recall that c squared. Now c, of course, is the focus for ellipses. C squared is the a squared take away b squared. And if you can't remember that, just remember that a is always larger than b, and c is going to be positive, or rather c squared is positive. So because a is larger than b, a squared take away b squared, it's got to be positive. So and then we've got plugging in c squared is equal to 25 take away b squared, which is 4. So c squared is 21. So c is equal to the square root of 21. Okay, now before we go farther, it's nice to identify some information about this ellipse before we look at the graph. And what I like to do is I like to create a column for what it would have been without the shift, without the -3 and the +5, and then create another column with what it is with the shift, which is what we care about. And the reason is because what I'm going to do is simply shift all these ordered pairs based upon these numbers here. So let me write the first column, let's call it old, and the next one will be new. So old will mean what you would have had if there was no shift, and new will be what you do have because there is a shift. And the things I'm interested in are the center of this ellipse. Okay, I'm also interested in the foci, the focuses, or the foci. Foci is plural, I guess. And then the vertices. Let me write this down here. And we're also going to be asked in problems you could be asked the length of the major axis. It's not uncommon to be asked that. And the length of the minor axis. Let's write that here. Okay, so let's see. If there was no shift, the center would have been 0, 0, right? That's always the case if there's no shift for our basic conic sections. Now new, because there is a shift, everything is shifted 3 to the right and down 5. So 3 to the right is going to make that a 3 and then drop this by 5. So the new center is going to be 3, -5. Now, whatever's in this column is what we care about, right? Because this is what we've got. But it's easier to take what we would have had and simply shift them using those values. Okay, foci. Now, remember the foci for an ellipse are positive, negative, c, comma, 0 from our video on ellipses. So in this case, it's going to be, well, c is root 21, right? So the foci would have been, let's write the negative one first, negative root 21, comma, 0, and then positive root 21, comma, 0. That's what we would have had if there were no shifts. Now with the shifts, you increase the x-coordinate by 3, and then you drop the y-coordinate by 5. So we're looking at 3 take away root 21, which is one of my personal favorite numbers. Then drop the y-coordinate by 5, and then the next one's going to be, well, 3 plus the square root of 21, comma, -5. And then the vertices, let's see, the vertices, of course, you have to think about the way this is oriented. And because A is A is always larger, but A occurs along the x-axis, that means this ellipse is elongated along the x-axis. That is, the major axis is horizontal. So the vertices are positive, negative, A, comma, 0 for an unshifted ellipse. So in that case, it'd be 5, 0, and then -5, 0. But then you shift everything, right? So add 3 to that, and you get 8. Then drop the y-coordinate by 5. And then you add 3 to this, and you get -2, and then drop that y-coordinate by 5. So there are our new vertices. The length of the major axis is always 2 times a. That hasn't changed, right? So if you simply imagine an ellipse, and then you simply shift it, right? Like, right 3 and then down, you don't change that length there, right? The length of the major axis is unchanged. It is a rigid structure. You're simply shifting the whole, imagine it's a piece of wire that's fixed. You're simply taking it, moving it over, and then shifting it down. So the 2 times a is going to be, what was our a? Our a was 5, right? So 2 times a, the length of the major axis is going to be 10, and the length of the minor axis, which of course is, this axis is the minor axis, that's 2b, because that's what b is, right? B is the distance from the origin to the shorter side of the ellipse. So b was 2, so it's going to be 2b, and that's going to make it 4. Okay, so with that information, let's go ahead and see what a graph of this looks like. So we're going to graph this on a program called Desmos. And so I entered the ellipse here. Desmos is a free online graphing calculator, which is great. So here's what I had in standard form, right? So I entered it at the end, and my graph is in red. Okay, this is the graph we care about. But I graphed this, let me just highlight this for you so you can see that's the one we care about. But I also put in this one for you, the blue one. And that's because this is the graph of what you would have had without shifts. So you can see that every point on this ellipse has been shifted to the right 3 and then down 5. Let's see, my scale is 2, 4, 6, 8, 10. So 3 is right here, right? And then down 5 would be right there. So this is the center, right? Every point has been shifted to the right 3 and down 5. My scaling makes it, let me see if I can find a better scale there. That's a little better. So let's see, I go right 3 and then down 5, and that gives me the new center. And the same is true with everything, right? Every point, this would be one of the vertices, right 3, 1, 2, 3, and then down 5, 1, 2, 3, 4, 5. Okay, so this red graph is the graph of my shifted conic. Okay, so what we see is that to get the graph, to determine if you're looking at a conic, what you have to do is complete the square. And in the next video, we're going to talk about how to take information about a conic and then from that create an equation. All right, until next time.